All right, we should be all set up. The interesting thing about time series is that we collect a lot of it, and we use it for, of course, a lot of historical reporting. And more, we're trying to use this data so we can do something at this moment in time. And in order to be really effective to do things in this moment of time, sometimes we have to do some predictions. And I think a lot of people get really excited about machine learning, but we want to actually give some props to Holt-Winters as well. And so with that, I'm going to let Anais talk a little bit about why Holt-Winters is a pretty cool thing to pay attention to.
Thank you, Chris. So before I start, I just want to get to know my audience a little bit better. So who here is a data scientist? Okay. Who here is comfortable with differential equations? Okay. You're my people. I like you. So today I'm going to be talking to you about when to use Holt-Winters over machine learning and when it makes sense and why it makes sense to do so. And Holt-Winters is a forecasting method, and it is also known as triple exponential smoothing. So if you hear triple exponential smoothing, just equate it with Holt-Winters. Before I go into it, though, I just want to give a little brief introduction about myself and share some pictures of my incredibly cute cats just to kind of warm up the room. I have 5 names, and so I had to pick some for LinkedIn. So if you want to connect with me on LinkedIn, and I encourage you to do so, you can find me as Anais Jackie Dotis. And then also, I love to make art, and I share a lot of that art in these slides. So if you're not a math person, I understand. I'm here to support you, and you can stare at the pretty pictures instead, and then just listen to the story about the math, and hopefully you'll gain something as well from this presentation. So the first time I ever gave this presentation, I was given this paper. First of all, who here is familiar with the M-comps? Okay, cool. So for those of you who aren't familiar, it's the benchmark for time series forecasting. And it happens, I think, annually. And the M3 competition happened in 2018. And this is a summary of all the results, where you can see that they are measuring the prediction error for several different types of forecasting methods, including purely statistical methods and purely machine learning methods. And what we'll notice is that all of the statistical methods or classical forecasting methods have lower prediction errors than the machine learning methods. And this includes things like RNNs and LSTMs, long short-term memory networks, machine learning algorithms and deep learning algorithms that are, or neural nets that are incredibly popular nowadays. And so, funny thing, or the thing I love about people and giving presentations, is that one time I gave this presentation, I think on June 20th, and on June 19th, the M4 competition had just come out. And someone came up to me and they're like, "You're wrong." And I'm like, "Yes, that's awesome. Tell me how else I can improve." And they are telling me that statistical methods suck. I love neural networks. Please don't continue giving this talk. And so I looked at the M4 competition results because they were telling me that the M4 comps revealed that, in fact, machine learning methods far outperform statistical methods. And it turns out that they're not wrong. They're definitely right. Hybrid methods outperformed any other method, and that method came from Uber. Also, side note, the M4 comps, they're pretty cool because they analyze, when they try and find the best forecasting methods, they analyze over or around 100,000 different types of time series data. So, you can really kind of be assured that no matter what type of time series data you have, this is a really excellent benchmark to base your opinions of the methods on. So what they found was that the hybrid method performed the best, but I've circled in orange. I don't know, who can see the orange circle? And people in the back? Okay, awesome. So that is where the first pure method pops up in terms of prediction accuracy. So it is a purely statistical method. And then in that column, there's several others that perform very well. And then at the very bottom in this blue box is when we finally get to see some pure ML methods that perform reasonably well. But still, there are a bunch of statistical methods that outperform all these purely machine learning methods. So I guess my conclusion that I have here is that if you have the resources, like Uber, to spend on developing your own hybrid method, then you should go ahead and do that if there's value for you for that. But if you don't have those type of resources, it makes sense to analyze kind of the cost to serve of your machine learning method and your machine learning approach and evaluate whether or not having a very slight increase in accuracy will actually affect your business decisions and bottom line. So I just wanted to credit the hybrid method from Uber. What they did is they took an RNN and they also combined it with exponential smoothing and changed the parameters for that method, that hybrid method, concurrently. And that was the one that won this year's competition. So before I begin and explain to you how it is that Holt-Winters works and how triple exponential smoothing works, I just wanted to take a step back and think about the most simple example of forecasting, and that is summarized by the naive method. And what naive said was that our forecast, y of t plus h, should be equal to today's value. Hold up, wait a minute. I'm going to go back because I want to talk about why it is that machine learning methods don't usually work very well for univariate time series data. I always forget to talk about this section sometimes because if you're working with statistics a lot, it might be on the forefront of your brain, but that's why we're here. And the short answer is that time series data is unique because it has a temporal element, which means that our y value, which we normally think of as an independent value, isn't truly independent. Those values are dependent. Time series has serial dependency. And more specifically, it has what's known as autocorrelation, which is a type of serial dependence, which means that our data is going to be correlated to itself in another point in time. And this attribute of time series data results in often overfitting, and also it violates an assumption of linear regression. So a lot of times when people are trying to evaluate the accuracy of their forecasting methods, they tend to use the R-square. And R-square is based off of linear regression. So if your time series data has autocorrelation, then you're going to find out that your R-square value will be very high, but that's actually wrong. So you can use other methods like the mean absolute percentage error to try and evaluate the accuracy of your prediction as well. But there are some problems with that too, because that will favor lower forecasts always. And so I think kind of the conclusion that I have with this part is that whenever you are performing any sort of analysis, it's always important to have statistics on the mind and consider the assumptions of any of the methods that you're using to evaluate your models. All right, so now we can talk about how it works. First of all, does anyone have any questions so far? Okay, cool, just checking. So the naive method just says that what happens tomorrow is going to be what happened today. And we might think to ourselves, well, that's pretty dumb. Why would someone want to credit themselves with such a simple model? But it turns out that even this can help uncover elements in our data that we might not be aware of if we hadn't done this simple analysis. An example I have for you all here today is that if we have a bunch of sales data and we apply the naive method to it, and we take the percent change, all of a sudden we realize that we have a dip in sales every 3 days. And so the naive method has helped us uncover seasonality. And that helps us set up for single exponential smoothing. So the idea here is if we can understand single exponential smoothing and how it works, then we'll easily be able to understand how triple exponential smoothing works. So single exponential smoothing agrees with the naive method in that we should probably look at our historical data to make a forecast, right? That's what forecasting is. But it goes one step further and says, let's take an exponentially weighted average of all of our past points and then use that as our forecast. And the way that this exponential mean is created is through alpha, which is known as a smoothing parameter. And alpha, and then, so you have this geometric sequence, alpha plus our last observation plus alpha times 1 minus alpha minus the previous observation before that plus alpha times 1 minus alpha squared plus alpha 1 minus alpha cubed, et cetera, et cetera. And it's these terms that actually create the exponential smoothing. And this geometric sequence converges to 1, which just ensures that our forecast will be on the same scale as our observed values. And it's important to notice, too, that alpha is much like a dial. And the closer that alpha is to 1, the more we're saying that we want the most recent observations to have the largest impact on our prediction. The closer the alpha is to 0, we're saying, no, let really historical data influence this next value that we're going to create. And that's evidenced by just the fact that if you look at the second term, alpha times 1 minus alpha, if alpha equals 1, then everything else reduces to 0, and we've just created the naive method again. And so you can see in this chart here, we have alphas. If alpha was 0.2, you can see how the transforms start slowly decreasing, and that's how they create exponential weighted mean. And if you summed up all the alpha transforms, they would be equal to 1, right? So everything's a remix, and mathematicians love to rewrite formulas and get more credit. And so one of the ways that Holt-Winters, triple exponential smoothing, single exponential smoothing, double, is often expressed is what's known as the component form. And they basically took this equation, which has a dot, 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 and wrote it in an iterative fashion, where we have our forecasting equation, y of t plus h, that's our forecast, is equal to our smoothing equation. And it's the same thing. The only reason why I'm introducing this is because in a little bit I'll show you what Holt-Winters looks like, and I just want you to be familiar with the notation. The next thing you might be thinking about, especially if you're mathematically inclined, is, all right, this is all great, but what do I select for my alpha, and what do I select for my L naught? In other words, what happens at time t equals 0? I know what my y of t is, but how do I create that initialization parameter? And I wanted to explain this optimization process. How does it we select the right alpha, the right smoothing parameter, and the right L naught through a math analogy. And the one that I've chosen is linear regression. Why? Because to me, the smoothing equation for Holt-Winters looks a lot like the point slope form of a line, right? We have LT, which is our prediction, which kind of looks like y. Alpha is a constant, so we can think of it as a slope. Y of t is our observations, or sort of like our x values. And 1 minus alpha times L naught, that all reduces to a constant, so we can just pretend that it's b. And so if we're going to do any sort of optimization, the first step is to define what we're optimizing for. And in the case of linear regression, that's minimizing the residual sum of squares. And all the residual sum of squares is the distance between every point in our data set and the line of best fit, and summing those values and squaring them. And if that meant nothing, that's okay, because I have pictures. So if this is our data set, we have a bunch of random points, and we draw some arbitrary line through it. We find the distance between every point and the line. We take that value, we sum them together, we square them, and we calculate an RSS. And then we do this again hundreds of times for different lines, and we get different RSSs, and we plot all of those RSS values against all of the various slopes and y-intercepts. And the result is a graph that looks like this. And at the very base of this graph is our optimal MMB, found through taking the partial derivatives. And so the reason why I wanted to even talk about this analogy is A, because it helps us truly understand, or my goal is that it helps us truly understand how the optimization works for Holt-Winters, but also because even though linear regression is oftentimes the first step that we take whenever we do any sort of data analysis, I feel as though its origins and how it operates is often taken for granted or neglected. And so I enjoy math. I really appreciate how simple and elegant this proof is and how it works. So I wanted to share it with you guys again. And then finally, I'm going to flash through the actual proof only to give us a sort of gut feeling for how even such a simple problem, something that we take for granted, is actually fairly difficult. And how we can't just use partial differential equations to find the optimum parameters for Holt-Winters. We'll have to use a numerical method instead. So that's what it looks like. It's pretty short, but you know, if you haven't done some partial differential equations in a hot second, maybe it's like, Lord, no thank you. So this is what Holt-Winters multiplicative method looks like. And you can see, for reference, we have single exponential smoothing on the bottom. So you can see how it looks really similar. The difference is we're adding 2 more parameters to our algorithm, and that is trend and seasonality. So the smoothing equation L naught is the exact same, pretty much. And we've added a B of t, and that represents the slope. And we've added a S of t smoothing equation, and that's for the seasonality. And because we're taking exponentially weighted averages of all those other components, we also need a smoothing parameter for the slope and a smoothing parameter for the trend, for the season. And we also need a B naught and an S naught. So we've basically taken our single exponential smoothing optimization problem where we only had to find an L naught and an alpha, and we've expanded it, so now we have to find 3 smoothing parameters and 3 initial parameters. So our problem has now grown from a 3-dimensional problem to a 6-dimensional problem, so we'll have to use numerical methods to do that optimization problem. Also, is there anything else I wanted to say about this? Oh yeah, okay, there's 2 other variables in here. There's K and there's M. And K is simply the index in the number of periods that you have in your season. So if you were forecasting sales, M might be 12 for each month. And if you wanted to forecast the sales in January, you want to make sure that your forecast is going to be made based on the appropriate period. So K is just an index that helps you keep track of where you are in time. So in this case, K would be 1. Last final point is that for optimizing Holt-Winters, people like to use the RMSE. The only reason why I'm bringing this up is because the RMSE is typically used in order to have a better idea of how to understand your error. When you take the square of something and then you take the square root of that, then you're on the same scale as your data, so you can help understand your error better. But what that also means is that now your optimization problem involves square roots, and your partial differential equations are even hairier. In fact, they're so hairy that you can't solve them. And so you have to use numerical methods. Who here is familiar with a lot of numerical methods? Yay, okay. Well, we wouldn't have the technology we have today without numerical methods. Numerical methods are just a tool or a math shortcut for finding approximations to solutions that, approximate solutions to problems that are really difficult. So a really common example is LU decomposition, and that allows us to solve a bunch of system of equations really efficiently and quickly. Instead of doing it the proper math way where you isolate each variable and then plug it into the other equation, which would take you hundreds of thousands of years to solve, what you do instead is you summarize your system of equations with a bunch of matrices, and then you do a couple multiplications and additions and subtractions, and then like magic, you've solved your system of equations in an instant. So it greatly reduces your execution time. And the numerical method that we use for Holt-Winters is known as the Nedler mean method. And the way that it works is that it places a simplex in that kind of bowl, but in this case it's 6 dimensions, but we'll just think of it as a bowl. And a simplex is just the closest representation of a triangle. So it places this triangle in the bowl, and the triangle's behavior is dictated by a for loop. And this for loop says, you know, take your values and order them in ascending order, and then find the smallest value, go closer to that, and then expand and contract, and then flip, and keep getting closer and closer to the optimal values. And what's really cool about the Nedler mean method is that while it's not actually a global optimization problem, it's really good at finding global solutions because of this expansion and contraction that it does. So if it isn't a local minimum, most likely at one point it's going to expand its area, take more points into consideration, and then realize, oh, no, I'm not at the global minimum yet. Let me keep going towards that correct spot. And then also there's the fact that the math is super easy. It's just a for loop. So the way that you do or apply Holt-Winters in Influx, probably the part that most of y'all care the most about, is really simple. So I'm first going to show it to you in InfluxQL because I recognize that not everyone is on the Flux train quite yet. And then I will show it to you in Flux afterwards, just so we have that point of reference. So this is my data set. And can anyone actually see it? I know people can't. Yeah? Awesome. OK. So it's just water levels in a creek in Santa Monica. And we can see that seasonality sort of solidifies around August 22nd, or sort of in the middle of the graph. So we will actually query our data from that point on. But the query to just generate this data first, this first visualization, is just select water level from my database and selecting H2O feet from the tag Santa Monica with this different times. And the first step to applying Holt-Winters is to summarize this data in as few points as possible. And the way that I'm going to do this is by using the group by function and the first function. And I'm basically going to take this season that has 2 humps and summarize it with 4 points. And so through visual inspection, I can see that at the base of one bump, or the minimum of one season, happens at 3:18, and then the next one happens at 9:36, and that is around, I think, 378 minutes. Again, I just did that through visual inspection, so I know that my group by is going to be a group by of that duration, and then I'm just going to apply the first function to that. Also, it happened to be that when I queried my data, I didn't query it exactly at the beginning of the season. So the orange here indicates an offset that I need to include in my fit. So in order to apply the first function, I just say select first of a water level from the database, and then I group by each point in between the hill and valley, which I found to be 379 minutes. And then it happens to be that my offset, again, I found it through visual inspection, is around 348 minutes. So I put that as the second variable in the group by. And then I just do select Holt-Winters with fit, and I apply that previous fit query inside the parentheses of the select Holt-Winters with fit. The only thing that I also need to include is how many seasons, or how many hills and valleys are in each season, which is 4, and how many points I want to predict, and I said 10. So the way that this is achieved in Flux, to me, reads a little bit more easily and is a lot easier. So I'm assuming here that I don't have an offset, so I just assuming that I have queried my data from the right time. All I have to do is filter by my field, and then I apply an aggregate window for the distance between each hill and valley, which is, again, 379 minutes. And I apply first to that so I can get the first value from that group by. And then I just feed that into Holt-Winters, and I say I want to output 10 points, and I know that I have 4 points in each season. And again, the interval for that is 379 minutes. If you want to access all of this information again, I wrote 3 blogs on it, so I recommend checking those out. And then if you want to learn more about autocorrelation, I have a blog about that. And then I forgot the author's name, but the final link here is a really good article that explains specifically the pitfalls of LSTM networks for univariate time series data, how to avoid them, and the proper steps that you should take in order to properly evaluate your time series forecasts. Finally, you can contact me at Anais at Influx, and if you have any questions about Holt-Winters or anything regarding Influx at all, please don't hesitate to ask questions on the community Slack or community page. Thank you.
Okay, Anais's people. Who has questions for her? You do have people.
Hi there, great talk. So can you go over again how you found the seasonality, like when you were on those, if you go back to your graph? Like it looks like there's two peaks, like bimodal. How are you figuring that out?
Just visual inspection. So I guess if you wanted to automate this for a lot of time series, I think an exciting thing about Flux would be that you could write a function that calculates the derivatives, and then you would know that, and maybe also the maximum value at those when the derivative equals 0, and then you could just write a function that determines what the seasonality is really easily, and then apply the output of that function to a series of Holt-Winters.
Okay, thanks.
Yeah.
I was just wondering how why you determined that offset the way you did. Why does it matter? Does it matter where in the season you start that? You just arbitrarily picking at the beginning of the day or at the low point?
It doesn't matter. When I first queried all my data, I saw that around like day 23, the seasonality really solidifies. So that's where I decided I wanted to take my forecasting, like use that data on for my forecast. And I just happened to like query some day, some point on the 23rd, and then I realized, okay, well it's not quite right, so I included that offset. But really, I think it makes the most sense to just kind of start your fit function at the exact time when your season starts.
So I'm curious, do you have to do that detection, you're reducing your thing to just 4 data points, or can you apply the Holt-Winters to the whole time series? Is that just a computational constraint, or will the technique actually not work?
I have never done it with the whole data set. I don't think that you can or should, because I think it just too much of a load, but I could be wrong. So, but yeah, I think just summarizing, less is more, because there's not really, I don't see an advantage to applying the whole data set for that fit. There isn't really one that I can think of. And then also, side note, if you set the group by interval to 0, then you have reduced Holt-Winters from triple exponential smoothing to double. So you're only accounting for the seasonality, and you've removed, or only for the trend, you've removed the seasonality. So if your data doesn't have any seasonal components, then you can still use Holt-Winters.
Okay, so you have to pick the number of seasons. It's not or you need a hyperparameter search to find them if you didn't want to manually input it.
Yeah, the hope is, I think, with Flux is that then, maybe in the future I can write a function that helps you find these, because these parameters are pretty easy to find, right? Mm-hmm. So you can do that, and then it would be automated. But right now, yeah, you have to do the work yourself.
Cool, thank you.
Mm-hmm. Thank you.
Is there an extension of the Holt-Winters algorithm for multivariate time series data?
No, because it doesn't really work that way. But if you do want a really good algorithm for multivariate, there's some really cool stuff being done with density-based. Okay, I can't remember the acronym, but it's DBSCAN with SVRs. And that's, I'm always for like the simplest approach, and the easiest approach is the best. But Allison gave an excellent presentation yesterday about how successful just using standard deviation was to find anomalies, for example. So the answer is no. You answered a really simple question. The answer is no, you can't. So in that case, I think it does make sense to use RNNs or LSTMs. And that's also the tricky thing with using ARIMA, right? Because like finding all the parameters for that is very labor intensive, so.
Thank you.
Yeah.
Lots of people, Anais.
Hi, can you use Holt-Winters for multi-season predictions? So I have maybe like a daily seasonality, but also a weekly seasonality. I would think a lot of like for our example, it would be like web traffic. There's during the day there is like a peak and a valley, but then also on the weekends is different than during the week.
For sure, I think you could just create 2 different fits and apply Holt-Winters to them separately. But for more complicated problems like that, and again, you don't have to use the first function to create a fit for your data. So whatever sort of way that you can summarize your data that makes the most sense is what you can use with Holt-Winters. But for especially for irregular time series, and for data where the seasonality varies a lot and there are exceptions to the rule, I always just point people to Profit because it's so easy to use and it does magic. So.
Any other questions? Oh, we have another in the front.
Okay.
Yeah, you just mentioned Profit. So how hard is that to integrate like outside libraries in with the new like Flux ecosystem or whatever you want to call it for doing these kinds of things?
I mean, I just use the client library, so.
In other words, you can import them somehow like a user-defined function kind of thing?
Makai, do you know the answer to that?
So I think what Anais is saying is she uses the client libraries to query the data and then use the libraries and Python rather than.
Okay.
Yeah. Thank you.
Yes, I think what Anais was saying was that she'll use the Python client libraries to query the code as well and then run the predictive stuff.
All right, if there's no more questions, we have a break, and then we'll be back here at 3:20 to go over Sam's talk on optimizing InfluxDB. And thank you, Anais, that was really great.